Hello friends, welcome to VTU EduShort program. So today I am going to discuss about numerical methods. Friends, module 2 numerical methods belongs to engineering mathematics 4 and I hope you know the subject code 15MAT41. So my name is Dr. S.S. Benchali, working as a professor in Department of Mathematics at Basaveshwara Engineering College, Bagalkot. I hope you know the contents of module 2 and first part is numerical method and second part is special functions. So I am going to handle these two parts. So in numerical methods, numerical solution of second order ordinary differential equations, Arangiakuta method and Milline's method. In part 2, special functions, series solution, Fibonacci method, series solution of Bessel's differential equation leading to Bessel's function, namely Jnx of first kind, basic properties, orthogonality, series solution of a Legendre differential equation leading to Legendre polynomial denoted by Pnx, and lastly I am going to discuss about Rodrigues formula. Okay, so when we observe these contents, so we will come to know that we are going to solve an ordinary differential equations using numerical methods and series solutions by Bessel's and Legendre methods. Right, friends, I hope now you are already familiar with differential equation. So you may ask, we are already familiar with some methods, namely variable separable method, homogeneous method and linear method, reducible to a linear method and exact method. So then you may ask, so why we want to study few more methods? So these methods are very much essential. So when we consider the applications, okay, before attempting a numerical method, now I wanted to verify what are the essential things we need to apply numerical method to a particular differential equation. So because I am going to solve a second order initial value problem by applying fourth order Arangiakuta method. So if I want to solve a second order initial value problem, so first I should know that how do we say that the given equation is an second order differential equation and what is the degree of that equation, whether the given equation is an ordinary differential equation or not. Sometimes we will say that some function is called the solution of the given differential equation. So how do we say that a function is the solution of the differential equation? Or sometimes I will ask, solve the differential equation, right? So what do you mean by to solve a differential equation or to solve an ordinary differential equation? So like that I can ask infinitely many questions on myself. Now first I have to answer for these questions. Okay, for these things you can refer these two textbooks. So one is Advanced Engineering Mathematics for Kreyszig, another one is Higher Engineering Mathematics by B.S. Grewal. Okay, what are the learning outcomes of this lecture? After the completion of a numerical solution of second order ordinary differential equations, Arangiakuta method and Milline's method, it is expected that a student will be able to do the following: be familiar with fourth order Arangiakuta method and Milline's method. So it means after solving an second order differential equation, you must be familiar with what do you mean by Arangiakuta method as well as Milline's method. Sometimes we will say that it is an second order Arangiakuta method, or sometimes I will say that fourth order Arangiakuta method. And what is the first order Arangiakuta method? I am going to explain all these things in the next few minutes. So, after the completion of this lecture, you will come to know that Rangakutta method of various orders and Milline's method, and you must be able to find out the numerical solution of a second order ordinary differential equation by fourth order RK method and Milline's method. Okay. As I have mentioned, what are the ordinary differential equations, or you may ask what are the prerequisites of an ordinary differential equation, right? ODE stands for ordinary differential equation. So, before that I can ask one simple question on myself. What is an equation? Before identifying the differential equation, I can ask what is an equation. I can say that an equation is a mathematical statement in symbols that two things are the same. Equations are written with an equal sign, as I have written 2 plus 3 is equal to 5. So, it means now I want to equate left hand side is equal to right hand side. So, this type of thing we call it as an equation, right? Or we can say that is a mathematical statement in symbols. We can use various arithmetic symbols, right? So, in this equation I have used only numbers, right? So, if you want, you can use variables also, right? Instead of numbers you can use variables. Say for example, here I have used 2 plus 3 is equal to 5, right? So, why we want to use only variables, right? So, now I want to use instead of constants I can use variables also. Say for example, x plus x is equal to 5 or x minus x is equal to 0, x minus x is equal to 0, right? Or you can write down x plus 1 is equal to some other number, right? So, like that you can use either equation. So, in equation either constants or we can use variables also, right? So, such type of things we call it as an equation when you want to equate left hand side is equal to right hand side, right? So, now I want to move into the next slide. We can define an differential equation, right? So, how do we find out the differential equation, or how do we identify an differential equation, or how do we find out an ordinary differential equation? Say for example, an equation may containing derivatives, as clear. Suppose derivative means so dy by dx. So, any equation containing dy by dx. So, such type of equations, so we call it as an differential equation, right? So, then we want to find out the order of the differential equation, is it clear? So, you want to identify the given equation. Say for example, a given equation is containing dy by dx. So, then I will call it as an first order differential equation. Suppose an equation containing d square y upon dx square plus dy by dx plus y is equal to 0, then I may call it as an it is a second order differential equation, is it clear? And similarly, an equation may contain d cube y upon dx cube plus d square y upon dx square plus dy by dx plus y is equal to 0. So, in this equation highest order derivative is d cube y upon dx cube, right. So, then I will say that it is a third order differential equation. Okay, right. So, like that you can find out the order of a differential equation, right. So, then how do you find out the degree of a differential equation? First you want to identify highest order derivative, then you can observe its degree, that is the degree of the differential equation. Say for example, d cube by upon dx cube and its power is 1, then you can say that so it is an third order first degree differential equation, right. Okay. Now, we are able to identify order and degree of the differential equation. Then how do you find out the solution of a differential equation? So, before that, as I have mentioned, so you are able to recognize an equation, right. So, how do you find out the solution of the equation? So, for example, now you are observing one equation, x minus x is equal to 0. So, it is also an equation. How do you find out the solution? So, if I replace x by 2, 2 minus 2, it will satisfy this equation, or if I replace x by 3, 3 minus 3, so 3 will also satisfy this equation. So, like that I can replace x by infinitely many numbers, all those numbers satisfy this equation. I will call it as an solutions of this equation. So, when we observe an equation like this, x plus 1 is equal to 2, right. So, if I replace x by 1, 1 plus 1 is equal to 2. So, if I replace x by any other number except 1, in that case those values will not satisfy this equation. It means the solution of this equation is x is equal to 1 only, right. So, what is our observation? If the equation is known to be true, it carries information about the value of x. So, in this case x is equal to 1. Okay. So, like that you can find out the solution of an equation, right. So, exactly in the similar way, now you want to find out the solution of a differential equation, right, or sometimes we call it as an what do you mean by solve an equation. In general, the values of the variables for which the equation is true are called solutions, right. To solve an equation means to find its solution. Okay. So, they have given a differential equation. Now, I want to find out the solution of the given differential equation, right. So, then you may ask, suppose if you solve an algebraic equation, so they have given a second order quadratic equation, right. So, if you find out the quadratic equation, I can obtain two values, right. Suppose if they have given a cubic equation, right. So, algebraic cubic polynomial or cubic equation. So, if we find out the solution, so what we will get? So, you will get 3 values in case of a cubic polynomial. Suppose if they give 4th degree polynomial, you will get 4 values, right. So, depending upon the values, we are able to write down the solution. Okay. How we are going to solve an differential equation, right. So, if you solve a differential equation, we will not get numbers. So, you will get a function. Then you may ask, what do you mean by a function? A function relates each of its inputs to exactly one output. It means for each input you will get one output. A standard notation for the output of the function f with the input x is denoted by using this symbol. The set of all inputs which a function accepts is called the domain of the function. The set of all outputs is called the range. What we have studied these things in the previous classes. Okay. So, for example, I can give one simple example, f of x is equal to x square. So, if I input 2, then I can obtain 4 as the output, and if I input 3, I can obtain 9 as the output. If I input 4, then I will get 16 as the output. So, like that, so for each input I will get an output, right. So, we can use functions in other fields also. Functions are used in every quantitative science to model relationship between all kinds of physical quantities, especially when one quantity is completely determined by another quantity. Thus, for example, one may use a function to describe how the temperature of water affects its density. So, instead of using F, we can use some words like temperature and density to represent a particular function. Okay. Now, how we are going to represent or denote a differential equation using various notations or various symbols. One notation is a Leibniz notation. So, sometimes we will write dy by dx or d square y upon dx square, d cube y upon dx cube, and so on. In general, d raised to n y upon dx raised to n, right? Or we can use prime notation, y single prime, y double prime, and so on. Or sometimes in some other textbooks you may find Newton's dot notation. So, for example, if you want to represent d square s upon dt square is equal to minus 32. So, it can be write down s double dot is equal to minus 32. Here f double dot represents d square s upon dt square. Suppose ds by dt is equal to minus 32, it can be represented by s single dot is equal to minus 32, or sometimes we can use some variables x and t, lambda, omega square. Sometimes the right hand side may be equal to 0, may not be equal to 0. Sometimes depending upon the problem we are going to use various notations like I, theta, mu, right, and so on. So, these are the different notations to represent an ordinary differential equations. Okay. So, you may ask, how do we recognize the given equation is an ordinary differential equation? Ordinary differential equation not involve partial derivatives. Suppose the given differential equation, if it does not contain partial derivatives, then I will call it as an ordinary differential equations, right. So, it involves a function of a single variable and the ordinary derivative of that function. So, sometimes given equation is called a partial differential equation, involves partial derivatives. As I have mentioned earlier, order of the differential equation is the order of the highest derivative. Okay. So, here they have given one equation d square y upon dx square plus dy by dx is equal to 3x into sin y. So, highest derivative present in this equation is d square y upon dx square. Therefore, it is an second order ordinary differential equation, right. So, this is an partial differential equation. Okay. So, now we are able to recognize ordinary differential equation as well as a partial differential equation. So, now I want to find out numerical solution of second order differential equation. So, before going to solve an second order differential equation, so why can't we think about ordinary differential equation, and suppose if we give first order differential equation. So, what is the geometrical meaning of first order differential equation, right. So, we are already familiar with derivatives. In calculus we have studied derivatives, right. So, how we are going to represent derivatives? Dy by dx of a differential function y is equal to y of x. So, what it gives? It gives slope of tangent lines at points on its graph. So, it means what is the geometrical meaning of differentiation? So, we will say that slope of tangent lines at points on its graph. What it means? Because a solution curve y is equal to y of x of a first order differential equation dy by dx is equal to f of x y is necessarily a differential function on the interval I of a definition. It must also be continuous on I. So, it means, so this is the given differential equation. How do we say that it is a differential equation? Because it is containing dy by dx. This is the first order differential equation. What we have assigned? We have assigned functions of x y to dy by dx. So, left hand side is dy by dx. Dy by dx means what? Slope. We have assigned f of x y to slope. what it means. So, we will find out this solution, or when we find out the solution of this differential equation, you will get the solution in a particular interval. In a particular interval means, so you can take an interval, so 0 to 1 or minus 1 to 1 or minus 2 to 2, or you can take 0 to infinity or minus infinity to plus infinity. So, in that interval, in any one of those intervals, we are able to find out the solution of this differential equation. Okay. Thus, the corresponding solution curve on I must have no breaks. I said that solution curve must be a continuous. Continuous means should not contain any breaks or any gaps. Must possesses a tangent line at each point. At each point means x comma y of x. So, that is the geometrical meaning of differentiation. The slope of the tangent line at x comma y of x on a solution curve is the value of the first derivative. The slope of tangent line at x comma y of x on solution curve is the value of the first derivative dy by dx at this point, and this we know from the differential equation f of x comma y of x. Okay. Say for example, here they have given a first order differential equation dy by dx is equal to 0.2 x into y, right. So, as I have mentioned, we are going to assign function of x y to dy by dx, where f of x y is equal to 0.2 into x into y at the point 2 comma 3. The slope of the linear element is, here linear element means, so we can find out a small tangent about a particular point. So, what we are observing in the diagram, so you will get a small line around this point. So, you can draw a tangent that we call it as an slope of a linear element, right. So, how do we calculate slope f of x y? I have replaced x by 2, y by 3, simplify, you will get 1.2. So, it means at this point, so when you calculate the slope, how do we, what is the slope? At this point, slope is equal to 1.2, or sometimes at this point, so you can draw the tangent, right. So, you can draw the tangent and you can calculate the slope. Slope is equal to 1.2. How do you get all these things? It is very simple. So, you know the various methods. By using various methods, you can find out the solution of this differential equation. So, you will get a solution. Solution means it is a function. When you draw the curves of that function, so it means you will get a family of curve, right. You will get a family of curve. For all those curves, at least one curve passes through this point. At that point, if you calculate the slope, what is the slope? Slope is 1.2. So, that is the meaning. Okay. Sometimes we need to find out a direction field. So, you may ask, what do you mean by a direction field? If we systematically evaluate a function f over a rectangular grid of points in the xy plane and draw a linear element at each point xy of the grid with slope f of xy, the collection of all the linear elements is called direction field or a slope field of the differential equation dy by dx is equal to f of xy. Friends, what it means? They have given a differential equation, right. So, differential equations behaves like a human being or any other existing system in the universe. So, it means, so this differential equation or any differential equation will change with respect to time, right. Suppose if I want to observe what is the behavior of a particular differential equation in a particular period, so that can be observed by drawing all linear element in a particular period. So, that we call it as that diagram, we call it as an direction field, or sometimes we call it as an slope field. So, for example, I have drawn the diagram of the same equation dy by dx is equal to 0.2 into xy, right. So, I hope now you are observing this diagram. What it represents? It represents behavior of this differential equation in a particular period. Is it clear? So, you can replace minus 4 by plus 4 or minus 6 by plus 6 along with the x and y axis, right. So, when we observe this diagram, so we will come to know a particular pattern. On the basis of this diagram, I can predict the solution of this differential equation. I hope you are observing a parabolic curve above the x axis and below the x axis, right. So, I hope I can observe on many curves. It means when you obtain the solution of this differential equation, you will get a function. When you draw the curve of that function, you will get a family of curves that can be observed or that can be predicted. So, this diagram is called slope field or direction field. So, before calculating the solution of any ordinary differential equation, first we can draw a slope field, then we can predict, then we will find out the solution, then we can compare. Okay. So, now we are already familiar with what do you mean by an ordinary differential equation, how do you find out the solution. Now, I want to introduce one more word, initial value problem. So, because now I am going to consider or I am going to solve an second order initial value problem using fourth order Arangacotta method. So, first I should know that what do you mean by initial value problem and what are the initial conditions, right. So, if I know these things, so very easily I can find out the solution of differential equation using fourth order RK method. Okay. So, before that here they have given dy by dx is equal to f of x y. So, clearly it is a first order differential equation. So, we may think of the equation 1 as assigning each x y in the plane of a slope dy by dx. So, it means as I have mentioned earlier, left hand side is slope and right hand side is a function of x y. So, now I have assigned f of x y to dy by dx. For the purpose of drawing a picture, it is more convenient to think of an equation as assigning to the point x y to the vector 1 comma dy by dx, right. So, what I will get, you will get a vector like this. So, that is the meaning. Okay. So, as I have mentioned, we can find out the solution of this differential equation, right, and you can draw the solution curve, you will get a family of curve. So, here they have given one condition, namely y of x naught is equal to y naught. So, it is called first order initial value problem, right. So, in this example, we want to find a solution of the differential equation on an interval I containing x naught, so that a solution curve passes through the point x naught y naught. So, here they are given one point and they are given first order differential equation. Suppose if I want to find out the solution of this differential equation, so that solution or at least one curve passes through x naught and y naught, that is the meaning. So, for example, all these curves are the solution curves of equation 1, right. So, at least one curve, say for example, this curve passes through the point x naught and y naught in the interval I. So, this is the interval I. So, this interval containing x naught. So, that is the meaning of dy by dx f of x y, y of x naught is equal to y naught. So, here also they have given dy by dx is equal to f of x y, y of x naught is equal to y naught, right. So, it is easy to interpret geometric terms. For one, we are seeking a solution of the differential equation on an interval I containing x naught, so that solution curve passes through the prescribed point x naught and y naught, as I have mentioned. So, exactly in the similar way, so you can consider second order initial value problem. So, observe this equation, highest derivative is d square y upon dx square, right. So, I will come to know that it is a second order differential ordinary differential equation. So, right hand side containing a function of x, y, y single prime subject to y of x naught is equal to y naught, y single prime of x naught is equal to y 1. So, in this example, we want to find a solution of a given differential equation whose graph not only passes through the point x naught and y naught. Earlier I said that they have given a first order differential equation, you will find out the solution, at least one solution must pass through the point x naught and y naught. So, in this case, so at least one curve pass through the point x naught and y naught, but passes through so that the slope of the curve at this point is y1. So, it means, so this is the given differential equation. So, you can observe the differential equation. So, we will come to know that without calculating the differential equation, you can say that solution of this curve or at least one curve passes through the point x naught and y naught, and if you calculate slope at this point, what is the slope at this point? So, y1 is the slope at this point. So, this much of information, so we will come to know from the given equation. Okay. So, what do you mean by an initial conditions? I said that y of x naught is equal to y naught is the given, right. The term initial condition derives from physical systems where the independent variable is time and where y of t naught is equal to y naught interprets the position of an object at beginning or initial time t naught. Suppose if they give this symbol represents what is the initial position of the object. Say for example, now you want to drop a pen, right. What is the initial position of the pen? How we are going to represent? So, y of t naught is equal to y naught. Is it clear? And another condition is y single prime of t naught is equal to y1. It represents what is the velocity of an object at a time or at some beginning. What is the initial velocity of the object? Is it clear? So, these two conditions will represent initial position and initial velocity of an object. Okay. So, now we are familiar with second order initial value problem. So, they will give a second order differential equation. Now, we want to find out the solution of second order differential equation. So, using numerical methods. Is it clear? Right. Okay. Now, you want to find out what are the advantages of numerical methods, or what do you mean by a numerical method, or you can ask, is it necessary to study numerical analysis, or you may ask why it is necessary to study numerical analysis. So, like that you can ask many questions on ourselves, then we can answer one by one. So, in the real world, no system behaves in a linear manner. So, we will when we consider any system, we will say that it is not in the linear manner. There is no ideal material. So, when you consider any material, you will not get an ideal material, ideal support conditions and a perfect structure. We will not identify a perfect structure. Due to imperfections of the behavior can always be described by a set of non-linear equations only. So, it means all these systems can be represented by using a non-linear equations. These equations cannot be solved analytically except in some trivial cases, and one has to resort to numerical analysis to find solutions. Nowadays, it has become an important tool to solve a wide spectrum of non-linear problems that arise in many physical situations. So, it means when we consider any real world system, that system can be write down in the form of a non-linear system of equations, then we will try with the known solutions. So, if it is possible to find out the solution of non-linear equations with the known method, in that case we will go for the numerical methods. By using numerical methods, we will find out the solution. Okay. Then you may ask, what are the numerical methods, right? So, for example, accurate simulation of dynamical processes related to planetary motion, chemical reactions, oscillations, turbulent flow, diffusion, transport processes and elastic stress require the knowledge of solving non-linear equations. So, by using various numerical methods, right. So, what are the numerical methods? Numerical analysis is the development of and study of procedures for solving a problem with a computer. It means numerical analysis means I want to write down the set of procedures. What is the first step? What is the second step? First I want to analyze the given problem. Then I want to split. Suppose if the given problem is a complicated problem, then that can be split into a number of parts. Then I will find out the solution by using a computer. That is why we will say that it is the set of procedures. Or I can say that numerical methods develop accurate and fast approximations to problems whose exact solutions are difficult to find because of their complexity. So, sometimes we are able to find out the solution analytically, or sometimes we are unable to find out the solution of the given problem analytically. In that case, we will search numerical methods. Is it clear? So, by using numerical methods, we will find out the solution, right? Okay. How we are going to find out the solution, right? So, now I want to find what are the advantages of numerical methods, right? So, first one is a major advantage for numerical analysis is that a numerical answer can be obtained even when a problem has no analytical solution. So, it means if you want to get a numerical no analytical solution, in that case also it is possible to find out the numerical solution. Numerical results can be plotted to show some of the behavior of the solution. Another important distinction is that a result from a numerical analysis is an approximation, but results can be made as accurate as desired. So, there are limitations to the achievable level of accuracy. So, because of the way that computers do arithmetic. So, it means suppose we have a problem. Now, I want to find out the solution by analytical method. Sometimes I am able to find out the solution by analytical method, or it may not be possible. In that case, I can go for the numerical methods and I can make it as an most accurate result 1. So, that depends upon the what type of equipments I am going to use. Okay. So, now I will come to the Arangyakutta second order method. Suppose if I want to study Arangyakutta second order method, we need some prerequisites. So, what are the prerequisites? So, one is Euler's method and another one is Taylor's method. So, we are already familiar with Euler's method as well as Taylor's series, right. So, understand the Arangyakutta second order method for ordinary differential equation and how to use it to solve a given problem. Okay. So, now I am going to consider a differential equation dy by dx is equal to f of x y, y of 0 is equal to y naught. So, clearly I will come to know that they have given first order initial value problem, right. So, now I want to solve this equation by Euler's method, right. So, what do you mean by an Euler's method? So, it is given that at x is equal to 0, we are the given value of y, or you can write down value of y is equal to y naught, or x is equal to 0, it is denoted by x naught. It means y is equal to 0 is denoted by y naught, x is equal to 0 is denoted by x suffix 0. Now, we know the slope of y with respect to x, that is f of x y. Then at x is equal to x naught, the slope is f of x naught y naught. So, it means they have given dy by dx is equal to f of x naught y naught, x can be replaced by x naught, y can be replaced by y naught. So, here sometimes instead of writing like this, so we can write down y of x naught is equal to y naught. So, both x naught and y naught are known from the initial condition. So, they will give x naught and y naught. So, we can use the initial condition. We can represent Euler's method graphically. Say for example, this is the true solution, right. So, you know x naught and y naught, x naught and y naught passes through the point. Now, by using the Euler's formula, we are going to find out y I. So, this we call it as an predicted value, and we can use the step length. So, here h represents step length, right. So, graphically we can represent Euler's method in this form. I will give some more inputs to the Euler's method, right. So, slope can be calculated by using the known formula. What is the known formula? Y1 minus y naught, x1 minus x naught, that is equal to, so you can write down, so f of x naught comma y naught, right. Thus, I can simplify. So, this can be written as y1 minus y naught is equal to f of x naught y naught into x1 minus x naught. What I have written here, y1 is equal to y naught plus f of x naught y naught in the form of x1 minus x naught. x1 minus x naught means what? I can replace the step length as I have shown in the diagram. The same formula can be write down, y1 is equal to y naught plus f of x naught y naught into h, right, or in general or in particular y2 is equal to I can write down y1 plus f of x1 y1 into h, or in general yi plus 1 is equal to yi plus f of xi yi into h. So, this is the general formula for Euler's method, right. So, here I can be replaced by some values. So, for example, now I will replace I by 0. So, what I can obtain? So, if I replace I by 0, 0 plus 1, y suffix 0 plus 1 means y1. So, that is equal to y suffix I. Y suffix I means I hope we will get y naught. So, f of x naught y naught into h, right. So, when we replace I by 1, I can obtain y2 is equal to y1 plus f of x1 y1 into h. So, like that you can replace I by 0, 1, 2, 3 and so on. So, you will get all the values as I have mentioned, y1 is equal to y2 is equal to y3 is equal to, right, or the values of the numerical or the values of the Euler's method. Okay, right. So, as I have mentioned, this graph or this line represents true value, and yi plus 1 is the predicted value, and this is the step size between xi and xi plus 1, right. So, earlier we have calculated yi, now we have calculated yi plus 1 at xi plus 1, that is the meaning. Okay. So, now you know the graphical meaning of Euler's method, right. So, now the Euler's formula derived from the Taylor series. I have already given Euler's formula, namely yi plus 1 is equal to yi plus f of x1 comma y1 into h, or xi yi into h. So, how do we get this formula? So, it can be obtained from the Taylor series, that is clear, right. So, and sometimes we will treat it as an first order RK method, right. So, Euler's formula is treated as a first order Runge-Kutta method. Now, exactly in the similar way, so we can define second order Runge-Kutta method. How we are going to define? So, sometimes we will write k1 is equal to h into f of x naught y naught. So, they will give a differential equation, and it is containing f of x comma y. F of x can be replaced by x naught, y can be replaced by y naught, h is the step size. So, using these values I can calculate a constant called k1, right, and similarly I can replace x coordinate by x naught plus h by 2, again h is step size plus comma y naught plus k1 is known, just now we have calculated, I can use k1 by 2. So, using these known values I can obtain another constant, say k2. So, y of x naught plus h is equal to y naught plus k2. So, this represents second order RK method. So, in the differential equation dy by dx is equal to f of x y, y of x naught is equal to y naught. X naught y naught is treated as the first solution or given solution or initial condition. So, exactly in the similar way, now you want to calculate what is the value of the function at x naught plus some increment, right. So, you will calculate using the right hand side function. So, exactly in the similar way, you can calculate higher values. Okay. Now, I will move into the Rangakotta fourth order method. So, they will give dy by dx is equal to a function of x y. So, y of 0 is equal to y naught. So, this is the given differential equation with the initial condition. So, now I want to find out the solution of this equation by using a fourth order RK method. So, what is the formula? Y I plus 1 is equal to y I plus 1 by 6 times of k 1 plus 2 k 2 plus 2 k 3 plus k 4 into h. So, you may ask what is k 1? K 1 can be calculated by the given function. So, f of x I y I. Here they have given f of x y is the given function in the differential equation, and they have given x naught and y naught. X naught is known, y naught is also known, right. So, when we replace x by x naught, y by y naught, so that is the meaning of x I y I or x 1 y 1. So, you will get the constant k 1, right. Okay. Now, exactly in the similar way, so you can find out k 2. How do you find out k 2? X 1 plus 1 by 2 times of h plus y 1 or y I plus 1 by 2 times of k 1 into h. Is it clear, right. So, by using this formula we can calculate k 2, right, and similarly, so you can calculate k 3 also. K 3 is equal to function of x 1 plus 1 by 2 times of h. So, y 1 plus 1 by 2 times of k 2 h, right. So, using this formula you can calculate k 3, right, and similarly you want to calculate k 4, right, x 1 plus h, y 1 plus k 3 into h. Using this formula I can calculate k 4, right. After calculating all the 4 constants, then I want to substitute those 4 constants in this formula, a general formula. I can obtain y I plus 1 is equal to, right. So, as I have mentioned in case of Euler's formula, here also I can replace I by 0. If I replace I by 0, all these formulas containing in terms of I, right. So, I can be replaced by 0, then I will obtain y 1 is equal to, right. So, if I replace I by 1, I will get y 2. So, I can calculate y 1, y 2, y 3, y 4 and y 5 so on. How I will get? By replacing I by 0, 1, 2, 3. So, then I can compare with various solutions. Various solutions means I can compare y 1 value with y 2, y 2 value with y 3 and so on like that. Is there any improvement or not? That can be observed by calculating various values. Okay. So, geometrically what it represents? Simply I said that I have to calculate k 1, k 2, k 3, k 4 and I said that I want to substitute those values in the formula. So, geometrically what do you mean by k 1? What do you mean by k 2? Right. Similarly, k 3 and k 4. So, they have given a differential equation, right. So, now you know the formula. So, you will calculate. So, k 1 means what? K 1 means this is the slope at x I. I hope now you are observing the curve. So, this is the curve at this point, this is the x 1 or you can treat it as an in general x I. So, at this point you can calculate the slope. How you are going to calculate the slope? So, by using this formula. Similarly, I said that you want to calculate k 2, right. So, what is the geometrical meaning of k 2? So, this is an estimate of the slope at the midpoint of the interval x I plus 1 using the Euler's method. Just now I have mentioned or we have discussed Euler's method. Using Euler's method, you can calculate midpoint, right. So, I hope now you are observing at this point you can calculate k 2, right. So, similarly, I want to calculate k 3. So, this is an improvement Euler's approximation for the slope at midpoint, that is the meaning of K3. Finally, I want to calculate K4. So, this is the Euler's method slope at xi plus 1. So, it means at this point you can calculate K4, right. So, friends, like that you want to calculate K1, K2, K3, K4, then you can substitute those values in this equation. I hope you will get the final solution, right. So, in the next session, I am going to solve second order ordinary differential equation using the same method, right. So, how we will get the solution and how we are going to compare with the real solution, we can observe all these things in the next session. Thank you.